Good evening, everyone. Welcome to our presentation on analyzing radio data from the Green Bank telescope to discover new pulsars. Our team members are Emma, Ellie, Payne, Ushi, and Nazreen, with mentorship from Miss Josephine. We start with a fundamental question: what are pulsars? Pulsars are highly magnetized rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. To discover new pulsars, we utilize several key data sources. Firstly, the Pulsar Search Laboratory makes data from the Green Bank telescope available to anyone who completes their course and gains certification. The Australian Telescope National Facility hosts an online catalog for all known pulsars, providing essential astronometric and spin parameters. We use 4 types of plots. Number 1, integrated pulse profile. This plot shows the signal intensity over time and frequency, helping identify the characteristic pulses of a pulsar. Number 2, sub-band plot. This plot displays the signal across various radio frequencies. A true pulsar signal should be detectable over a broad range of frequencies. Number 3, time domain plot. Folded data chunks stacked over time reveal the periodic nature of the pulsar signals. Number 4, dispersion measure plot. This plot shows the amount of interstellar gas affecting the signal. Real pulsars have a measurable dispersion.
In our technological age, manually grading candidate plots is too cumbersome. For that reason, we designed a machine learning algorithm, specifically a convolutional neural network, to distinguish pulsar and non-pulsar plots. What is a CNN? It's a neural network architecture commonly used in computer vision, a branch of AI that deals with image classification. First, convolution layers apply filters to the input image to extract features, creating feature maps which serve as input for the next layer. This enables the CNN to gradually build a hierarchical representation of the image. Next, the pooling layer reduces the size of volume, which makes the computation fast, reduces memory, and also prevents overfitting. Then it goes to the dense layer, which is used to classify images based on outputs from convolutional layers. The nature of the architecture allows it to handle large amounts of data and achieve high accuracy when detecting patterns and features in images. This makes it perfect for our project, and is further illustrated by producing the best results among other tested methods.
So firstly, the data sets and procedures. The model was trained on for plot graphs from the AO237 survey database, pulled directly from the PSC site in a PNG format. The code basically compiled the original complete graphic, cropped out the 4 fundamental plots, and finally made the merge plot of just the 4 plots. The procedures, the ML models were coded on Google Colabs using the Python programming languages and the environment set up by installing and importing packages and libraries as needed. So the fun part, programming and modeling tasks. Firstly, we need to import the dataset. So we build a data pipeline between Notebook and Drive and use the tf.keras.utils.image dataset from directory function to access or grab the data through the pipeline and use NumPy to iterate through to form batches. Secondly, pre-processing, basically making the data ready to be input into the model by doing essential things like resizing and using the .map function to divide pixel values by 255, thereby effectively normalizing the values between 0 and 1. Thirdly, splitting the dataset. So we use the .take and .skip functions to split the data, whereby 70% is allocated for training, 20% for validation, and 10% for testing. 4, building the model. So this is where the magic actually happens. In our model, we use 3 convolutional layers, 3 max pooling layers, 2 dense layers, and 1 flat layer with the use of an atom optimizer and a binary cross-entropy loss function. And finally, actually training it. So we fit our model with training data and run for 20 epochs, that is 20 runs around the entire training data. So what were our results? To evaluate, we loop through each batch in our testing data and use the model.predict function to make predictions. That is, compare the y-hat value, which is what the machine predicted, with a y-true value, which is the actual answer. Now, to gain insights into how our model is actually performing, we utilize matplotlib to visualize our training and validation loss and training and validation accuracy. As you can see, there's a general decrease in loss and an overall increase in accuracy, though more haphazard. And finally, a test. So at the start, we kept 5 or 6 plots completely separate from the database. This is the data that the computer has never seen before. And in this particular trial, we imported a pulsar test example, which it successfully classified as a pulsar. Ultimately, our model was able to achieve a prominent accuracy of 100%, which we'll discuss more about what this means and what we infer from it in the discussion section.
Now we're going to talk about pulsar candidate plots. Over the summer, we analyzed and hand-graded over 2,000 candidate plots from the Pulsar Search Collaboratory. So we found two potential pulsar candidates. The first one has a DM of 20.4, which is similar to the pulsar above, which had a DM of 19.8. And there were faint vertical lines at 0.5 and 1.5 for the time domain and subband plot. And the pulses were also periodic. However, when we set this to the PSC, they said this was unlikely to be a pulsar candidate. And the next one had a DM of 28.3, which is similar to the pulsar we found, which had a DM of 26.1. There are also faint vertical lines at 0.5 and 1.5 for the time domain and subband plot, and the pulses are also periodic. This plot is like the trademark plot for an RFI. There is a very visible dark horizontal line on the subband plot, which is characteristic of an RFI. And the DM is 0. And the next plot is the noise plot. The time domain and the subband plot is very static, and there are no visible horizontal or vertical patterns. And the DM of 1379 is too high to be a pulsar or an RFI.
So then our discussion and future work. As mentioned earlier in the CNN, we said that our CNN achieved an accuracy of 100%. But how did that work and what exactly does that mean? So during the process, one of the restrictions presented was by the aggregate data available to us, because we had access only to plots from the AO237 survey and public databases, which largely included extremely strong and ideal pulsar plots. It was super good in distinguishing the really good plots, but not as good in the less than perfect plots. That's why for our future work, we plan to acquire and include plots of more borderline pulsars to enrich our pool of data, and hence enhance the model's performance as a robust and generalized algorithm. For the pulsar candidates, the PSC will be looking further into the maybe plots, which means possibly it could find a promising candidate or perhaps even a real pulsar from one of our graded plots. Thank you for listening.